Welcome to the deep dive. Today, we've got a massive stack of sources engineering memos, articles, expert analyses.
A lot to get through.
A lot. And our mission today is really to cut through the noise on generative AI and just focus on the core concepts you actually need to build things. We want to understand the architecture, the scaling problems, and the toolkit that's defining this new era.
And you mentioned an important term there, this idea of an era. We're in the era of foundation models.
Right.
And that's the key because it defines the shift. Historically, ML engineering meant training a model for one specific task.
So one model for spam, a totally different one for summarizing a news article.
Exactly. From the ground up, AI engineering is the opposite. It's about leveraging these enormous pre-trained general-purpose models, LLMs for text, LMMs for image and video, and just adapting them.
And it felt so sudden for everyone. We call it the ChatGPT moment. But the sources, they remind us that the basic idea that making models bigger makes them better, that isn't new at all.
Not at all. The pioneers behind AlexNet were saying that way back in 2012.
So what was the shock?
The shock wasn't the capability itself, but just the sheer overwhelming wave of applications that this scaled power suddenly unlocked for everyone.
And that shift in focus from building to leveraging has created maybe the fastest growing engineering field in history.
Oh, for sure. The pace it's just staggering.
Here's a number that jumped out at me from the source material. Open source AI tools. Think LangChain, AutoGPT, Alamaham. In just 2 years, they've already blown past Bitcoin in GitHub stars.
Wow.
And they're on track to surpass giants like React and Vue. When you see that kind of velocity, you know something fundamental has changed.
And to understand that momentum, you have to look at the, let's call it the physics of how we got here.
The physics of scaling.
Right. I mean, language models have been around since the 1950s. Claude Shannon was writing about them. But they only took center stage recently because they solved the biggest problem in traditional ML.
The data labeling bottleneck.
The data labeling bottleneck. The need for armies of humans to sit there and label everything. This is a cat. This is fraud.
Tedious, expensive work.
Incredibly. But language models can use what's called self-supervision. The labels are basically inferred from the text itself.
So like filling in a blank in a sentence.
Exactly, or predicting the next word. It allows you to just scrape the internet for hundreds of billions of tokens of data without paying a human to label any of it.
And when we talk about scale, the metric is parameters, right?
Yeah,
These are the variables the model updates during training.
They are. And for context, our sources note that in 2018, the first GPT model had 117 million parameters. That was huge then.
And today?
Today, a model isn't really considered large unless it's hitting 100 billion parameters, maybe more.
That's a 1,000-fold increase in just 6 years. It's wild.
And it's not a random increase. It's all governed by what's known as the scaling law.
Okay, so what's the law?
It basically dictates that model performance is this tight relationship between three things: model size, dataset size, and compute. Teams use their compute budget to find the sweet spot.
The compute optimal model.
Precisely. The perfect balance of size and data to get the most performance for every dollar you spend on training.
But the sources also make it clear that raw performance isn't always the most important thing in the real world. There's this trade-off with usability.
A huge one. I mean, take the llama models. Meta could have trained them to be bigger, to be technically compute optimal.
But they didn't.
They intentionally chose a slightly smaller size. So, by the strict definition of the scaling law, performance was suboptimal.
Why would they do that?
Because a smaller model is way more usable for the average developer. And crucially, the inference costs, the cost to actually run the model, are dramatically cheaper. That decision led to massive adoption.
That kind of trade-off, that balancing act, it seems like it's about to become mandatory because we are heading straight for some huge bottlenecks.
Two profound ones, and this is where the engineering challenges get, let's say, existential.
Okay, what's the first one?
It's straightforward, but also terrifying. Data scarcity.
We're running out of data.
We are running out of high-quality, human-generated internet data. The models consume it so fast that some projections show we hit the wall in the next few years. We just can't write new, good, diverse text fast enough.
Running out of the raw material of human thought. That is a strange concept. So if we run out of human data, where do we go?
And that leads right into the second bottleneck. Data contamination, or what some researchers are calling the curse of recursion.
Recursion.
Yeah. The internet is now being flooded with AI-generated content, blog posts, summaries, articles, you name it. If we start training the next generation of models on that synthetic data.
You're training on the output of the last model.
Exactly. And that can cause something called model collapse.
What does that collapse actually look like? Is it like a crash?
No, it's more of a gradual decay. It's slow. The model starts to forget the original true data patterns. Its outputs get repetitive, they lose creativity, and you get more and more nonsense. It's like making a photocopy of a photocopy of a photocopy.
Each generation gets a little worse.
Till it's just mush.
That is a little alarming. So if the quality of the data going in is a huge problem, we have to be just as worried about how we judge the quality of what's coming out.
And the sources are unanimous on this. Evaluation is one of the single hardest challenges in AI engineering today.
Because it's so open-ended, right?
It is. If you're building a fraud detection system, it's a closed task. It's either fraud or it's not. There's a ground truth.
But for a chatbot, if you ask it to explain a concept, there could be a million perfectly good answers.
A million valid responses. So you can't just compare it to one reference text. You have to move beyond that kind of exact evaluation and into, well, subjective evaluation.
And the most popular solution here is also kind of controversial.
It is. Using AI as the judge.
AI evaluation.
Right. You take a stronger model, say a GPT-4, and you use it to score the response from a smaller or a newer model. You ask it to rate things like factual consistency, toxicity, coherence.
The logic being that judging is an easier task for an AI than generating something new from scratch.
Generally, yes. But trusting an AI to grade another AI, as you can imagine, introduces its own weird biases.
What are the big ones to watch out for?
The research highlights two really interesting ones. The first is position bias.
Right.
If you give an AI judge two answers to compare side by side, it overwhelmingly favors the first one it's shown.
That's fascinating because it's the opposite of humans. We tend to have a recency bias, favoring the last thing we saw.
It's the complete opposite. So if you're an engineer, you have to constantly randomize the order of the answers you're testing, or your results will be skewed.
What's the second bias?
Verbosity bias.
Wow.
The stronger models, they like long answers. They will often give a higher score to a longer 100-word response that has factual errors
Over a shorter one.
over a short, concise 50-word answer that's perfectly correct. The AI seems to equate length with depth, even when it's wrong.
Which makes measuring factual consistency the most important thing incredibly hard.
It does, so engineers have to get very systematic about it. We split it into local and global consistency.
Local means checking against the context you just provided in the prompt.
Exactly. And global means checking against, all of human knowledge, the real world.
So how do you actually catch a model when it's just making stuff up?
One of the coolest techniques is called self-verification. The model generates an answer, and then it stops. It decomposes its own response into individual facts.
It becomes its own fact checker.
It does. It then uses search or other tools to check each statement one by one before giving you the final answer. It's expensive, but for high-stakes applications, it's necessary.
This brings us right to the practical side of things, building the systems. Our sources really focus on two main ways to adapt these foundation models for a specific use.
Retrieval augmented generation, or RAG, and fine-tuning.
Let's start with RAG.
So RAG is your go-to for grounding a model in facts it doesn't know. It's a two-step process. First, retrieve relevant info from an external source, your company's documents, a user manual.
And that data lives in these huge vector databases, right?
It does, and this is where algorithms like approximate nearest neighbor, or ANN, come in.
Why is that approximation so important?
Because searching billions of vectors for an exact match is just too slow for a real-time chat application. ANN gives you incredible speed by sacrificing a tiny bit of perfect accuracy. It's a critical engineering trade-off.
So RA retrieves the facts, and then the model generates an answer using only those facts. The benefit seems obvious.
Yep.
It keeps the model up to date, and most importantly, it reduces hallucinations.
Massively, because the model is grounded in real context you just gave it.
Okay, so that's RAG. What about the other method, fine-tuning?
Fine-tuning is different. You're actually continuing the training process on a smaller specific data set. You are permanently changing the model's internal weights.
So as an engineer, what's the simple rule of thumb for when to use RAG versus when to use fine-tuning?
It's actually pretty simple. RAG is for facts.
For knowledge.
For knowledge. If your model doesn't know about your latest product, you use RAG to give it that information. fine-tuning is for form,
For behavior.
for behavior. Do you need it to always sound like your corporate brand voice? Do you need it to consistently output structured JSON? Do you need it to learn a special syntax, like how to code in a specific way? That's all fine-tuning.
But fine-tuning these massive models used to be prohibitively expensive, right?
Oh, absolutely. The memory and compute requirements were just out of reach for most people.
And that's where another innovation came in.
This is where parameter-efficient fine-tuning, or PEE, changed the game. The most popular method by far is LoRA, low-rank adaptation.
And how does LoRa work without retraining everything?
Instead of updating all 100 billion parameters, you freeze the original model, and you only train a tiny, tiny subset of new parameters.
And you target the most important parts of the model's brain, so to speak.
You do. Specifically, the key and value matrices in the attention layers. It's based on this mathematical insight that you don't need to change everything to capture the essence of a new behavior.
The big benefit being
That you end up with these tiny, lightweight adapters. They're small files you can easily swap in and out. So a company can run one single large model and then dynamically load dozens of different LoRa adapters for different tasks without needing dozens of copies of the full model.
it's incredibly efficient.
Very.
And whether you're using RAG or fine-tuning, the sources all come back to one thing. Proprietary data is the new competitive moat.
Which brings us to the data flywheel.
Absolutely. User feedback is the fuel. And the most valuable kind of feedback is when a user actually corrects the AI's response.
Because that creates preference data.
It creates perfect preference data. The AI's original answer is the losing response, and the user's edited version is the winning response.
Yeah.
That pair is gold for alignment training.
That's how the models actually learn to be more helpful over time.
It's the core of it. Okay, let's look forward a bit. We're moving beyond simple question and answer. We're moving toward autonomous agents.
From query response to systems that can plan and execute actions.
How do we define an agent?
An agent is just a model plus an environment and a set of tools. The tools could be a calculator, a search engine, a code interpreter. The LLM acts as the planner. It looks at the goal and figures out the sequence of tool uses to get there.
So if I ask it, what was Apple's stock price on the day the Eras Tour started?
It won't just guess. It'll plan. Step 1. Use search to find the tour start date. Step 2. Use a financial data tool to get the stock price for that date. It's orchestrating tools.
Now, there's a debate inside the community about whether these models can truly plan.
There is. Some argue that because they're auto-regressive, just predicting the next word, they're just recalling knowledge about plans they saw in training, not actually planning novel solutions.
But in practice,
In practice, simple techniques like chain of thought, just telling the model to think step by step, massively boost their planning ability.
and building these complex agents requires a much more sophisticated architecture.
Oh, way more. You have to start adding layers. You need your context construction, of course, but then you need multiple guardrails.
For input, output, toxicity.
All of it. And you need smart model routing, a gateway. You don't want to use your most powerful, expensive model for a simple query.
So you route simple tasks to cheap models and complex ones to the big guns.
And you absolutely have to have caching, both exact caching for identical queries and semantic caching.
Where you use vectors to see if a new question is close enough in meaning to an old one.
Exactly. It's essential for managing cost and latency in a multi-step system.
And with all this complexity, observability and monitoring become non-negotiable.
They have to be. With these agentic loops, you have to be able to detect when something goes wrong. If your retrieval quality in your Argy system drops by just 5%, the whole agent can fail. You have to catch that immediately.
So let's synthesize this for everyone listening. What are the key takeaways?
I think the biggest one is that the focus has completely shifted. Building real-world applications is now about AI engineering. It's about adaptation, evaluation, and system design, not just training.
And the rules of thumb are pretty clear.
They are. RIG is for facts, for external knowledge. Fine-tuning is for form, for style and behavior. And robust evaluation, even with imperfect AI judges, is absolutely mandatory to make sure your output is high quality.
So we started this by establishing that scaling models with high-quality data is what created this entire revolution. But we also learned that we're quickly running out of original human-generated text. And we face this risk of model collapse from recursive synthetic data.
The great bottleneck.
Right. So if high-quality non-recursive data is truly the limiting factor for future performance, we have to ask a different kind of question. What kind of entirely new data acquisition strategy will unlock the next generation of AI? Will models have to, I don't know, learn from physical embodied experience in the world rather than just from static text?
That is a fascinating prospect.
Thank you for the deep dive.
Always a pleasure.